In this section, we're going to be looking at the stoichiometry of reactions in aqueous solutions and something called titrations. We've actually covered titrations a little bit with the fundamentals. So the goal is to explain how a titration is carried out and explain the procedure for standardization of a solution and calculate concentrations or amounts of reactants from titration data. Okay, so titrations. It's a method of chemical analysis. And this method is common for weak acid or weak base analysis. If we take a look at a strong acid, the hydronium ion concentration is equal to the strong acid concentration because of complete ionization. So therefore, if you measure the pH of a solution, you can use that to calculate the hydronium ion concentration, and there you go. Or conversely, you could use the hydronium ion concentration to predict the pH. Easy peasy. Weak acids, on the other hand, the hydronium ion concentration does not equal the concentration of the weak acid because of incomplete ionization. And in fact, the amount of hydronium ion is going to be much less than the concentration of the weak acid. So how do you determine the concentration of a weak acid in solution? And the answer is you have to titrate it. You do a reaction where you get the weak acid to react completely and quantitatively with a strong base. So this sounds like the analysis that we did before for an analysis of a mixture and an analysis of a pure compound to get the formula. You need a reaction that reacts completely and quantitatively. Now, more about titrations. You begin with a measured amount of solution, let's say an acid, a weak acid. You add base to the solution until it is neutralized. This point where it's neutralized is called the equivalence point. It's also called an endpoint. And we don't want to add base to the solution until it becomes basic, because if you add too much base, it will become basic, just till it becomes neutral. So when you reach that equivalence point, that's when there's a stoichiometric equivalence between the reactants. Notice I didn't write that there is an equivalence or an equality between the reactants. It's a stoichiometric. So it's based on the stoichiometry of the reaction. For instance, in this reaction here between this acid, nitric acid, and this base, sodium hydroxide, to make water and sodium nitrate, the ratios are 1 part acid to 1 part base, or 1 mole of nitric acid to 1 mole of sodium hydroxide. That's the equivalence point, 1-to-1 ratio. But suppose we had nitric acid reacting with calcium hydroxide. In this balanced reaction, there are 2 moles of nitric acid for every 1 mole of calcium hydroxide to reach that neutrality point where you just get water and a salt. So here, the equivalence point, the endpoint, would be when there are 2 moles of nitric acid for 1 mole of calcium hydroxide. So that's the equivalence here. So the equivalence does not mean a mole, 1 mole to 1 mole. It means whatever the coefficients are, that's how many moles to how many moles when you reach the equivalence point. So here's another aspect of titrations that we need to be concerned with, and that's recognizing the equivalence point. How do you know when you've reached the endpoint? And with the acid-base titrations, we usually use a color change using the pH indicator. But let's say that it's not an acid-base reaction, but it's a reaction that forms a precipitate. Maybe it's the formation of a precipitate. Or you might be titrating a solution that is kind of cloudy, so it's not really a solution, it's a homogeneous mixture, and you titrate it till it becomes clear. And there are other ways of doing titrations where you are looking for some sort of indication that you reached the equivalence point. If you don't have a way to see the equivalence point or recognize it somehow, then it's going to be very difficult to determine any sort of quantitative material from the titration. Okay, let's take a look here. This is an example of an acid-base titration. So a 1.034 gram sample of impure oxalic acid is dissolved in water and an acid-base indicator added. the sample requires 34.47 milliliters of 0.485 molar sodium hydroxide to reach the equivalence point. What is the mass of oxalic acid in the sample, and what is its mass percent? So I'm going to go ahead and start this with this. We want the mass of oxalic acid. And you want the mass percent oxalic acid. And the mass percent of oxalic acid is going to be the mass of oxalic acid over the mass of the sample times 100%. And we actually have the mass of the sample. I'm going to put that that's a 1.034 grams. Okay, so here, it turns out if we get the mass of oxalic acid, we'll be able to get the mass percent very easily. Okay, so the other thing that we're going to need here is we're going to need a balanced reaction. So what's the formula for oxalic acid? Well, that's something you may have to look up. It's based on the oxalate ion. The oxalate ion is C2O4 2-. So what is the formula of the acid if that's the oxalate ion? It's probably going to be H2C2O4. So how do we confirm that? I'm going to look at my book. I'm going to go to the index, and I'm going to see if they have anything about oxalic acid. So OP, here we go, oxalate ion, and oxalic acid. So oxalic acid, they have the molar mass of, structure of, and so forth and so on. I'm going to go to page 92 and page 140 and see what's up. So page 92 or page 140. I'm going to go to page 140 because that happens to fit into the chapter we had previously done. So when I look at oxalic acid, sure enough, it is H2C2O4. Okay, so you can always look these things up in your book if you need to. On the exam, this would be a formula you would not expect to know. I would not expect you to know, and I would give this to you. So if we write out the balanced reaction without regard for the states, we have oxalic acid, H2C2O4, reacts with sodium hydroxide to give water and a salt. Now here we have two hydrogens that are going to react with two hydroxides, but here I only have one hydroxide, so I'm going to put a 2 here. Two hydrogens and two hydroxides will make two H2Os. We have remaining two sodiums, so there's the two sodiums, and one oxalate. So there's your balanced reaction. And here we have 34.47 milliliters of the sodium hydroxide solution with a molarity of 0.485 molar. And we have the gram sample. So here, I have this ratio here, and I have this gram sample here, and I have the milliliters here. So what do I want to start with if I want to get to the mass of oxalic acid? So here I'm going to put mass of oxalic acid. So how am I going to get there? Well, to get to the mass of oxalic acid, about the only way I know to get there is to have the moles of oxalic acid. So how am I going to get to the moles of oxalic acid? I have the feeling here, if I have a volume and a concentration, I should be able to get the moles of sodium hydroxide. And I can get the moles of sodium hydroxide, then I can get the moles of oxalic acid because I have a balanced equation. So how am I going to get my moles of sodium hydroxide? Well, I'm going to use the concentration and the volume of my sodium hydroxide. Okay, So here, if I'm going to use the concentration and the volume, here's the volume, here's the concentration, what do I want to start with? Do I want to start with the concentration, which is a ratio, or the volume, which is not a ratio? I'm going to start with the volume. So I'm going to map this out here as the volume of sodium hydroxide, and that's in milliliters. We're going to turn that into a volume of sodium hydroxide in liters, and then we'll turn that into moles of sodium hydroxide. So we have 34.47 milliliters of sodium hydroxide solution times 1 liter of sodium hydroxide solution per 1,000 milliliters of sodium hydroxide solution. Let's see, I'm going to tilt this a little bit. And then to turn this into moles of sodium hydroxide, I'm going to multiply by 0.485 mole of sodium hydroxide per 1 liter of sodium hydroxide solution. Okay, so here, these things are canceling. Boom, boom, boom. And then next, I'm going to use my mole ratios from the balanced reaction, which says 2 moles of sodium hydroxide and 1 mole of oxalic acid. Okay, but remember, we want the mass of oxalic acid, so we're going to have to multiply by 1 mole of oxalic acid on the bottom, and we need the molar mass of oxalic acid. So we have 2 hydrogens, which is 2.016, clear. So we have 2 hydrogens, which is 2.016 grams, plus we have 2 carbons, which is 24.02 grams, plus we have 4 oxygens, which is 64 grams. Oops, I got to go back. So 64 plus 24.02 plus 2.016, and so 2 plus 24 is 26. 26 plus 64 should give me what? 70, 80, 90? So here we go. 90.036. So I'm going to put 0.4 grams of oxalic acid. Okay, so let's go ahead and do the calculations here. I'm going to go ahead and estimate very quickly. So I think we can all agree that 90 is pretty close to 100. So 100 goes into 100 10 times. So now I have 10 on the bottom here. 10 will go into 34 3.4 times. Now honestly, if this is 90, it probably goes in here about 11 times, and 11 goes into 34 about 3 times. So 3 times half is 1.5, and 1.5 divided by 2 is about 0.75. So that's an ish, 0.75 grams of oxalic acid. So let's go ahead and put in the calculations here. So I've cleared it. 34.47 times 0.485. Oop, I put a 6 there. Trying to get it so you can see the numbers. There it is, 0.485. And then times 90.04. And then we're going to divide by 1,000. And then we're also going to divide by 2. And we get 0.75. Wow, the guess was pretty close this time. 0.75. Here we have 4 sig figs. Here we have 3, infinite, infinite, and 4. So we get 3 significant figures. So 0.753 grams of oxalic acid. So that certainly takes care of one of my wants, but I still have to calculate the mass percent. So to calculate the mass percent of oxalic acid, we're going to take that 0.753 grams of oxalic acid and divide it by the mass of the sample and multiply by 100%. And here we're going to estimate again. I think we can all agree that 0.75 out of 1 is about 75%. Okay, so 0.753 divided by 1.034 and times 100, and I get 72.8% oxalic acid. Okay, there we go. There is your acid-base titration. Now, oftentimes, when you're doing an acid-base titration or a titration, you need to standardize an acid or base. So you want to react an acid with the base to find out maybe the concentration of the base, or a base with the acid to figure out the concentration of the acid. But you need to know something about your beginning material. So if you titrate an acid with the base, you want to know something about the base. To standardize a base means to figure out its concentration. So usually when you try to standardize an acid or a base, you react it with the opposite. If you have a base, you react it with an acid. If you have an acid, you react it with a base. And you do this so that you can find the concentration of that particular base or acid. That's called the standardization. Now, you don't want to standardize it with another solution because you're not sure about the concentration of that solution. So what do? You titrate it with a solid acid or a solid base. And these are easy to come by. And you react to an equivalence point, which is a stoichiometric equivalence of acid and base. You need to know when the equivalence point is reached, also called the endpoint, and usually it's noted by a pH indicator. Okay, so what makes this different than a acid-base titration is that usually you're going to titrate, if you will, or standardize against a solid base or a solid acid. The reason being is that it's easy to weigh the solid acid or the solid base and know precisely how much acid or base you have. Whereas if you have a solution, you're not sure of the concentration, you don't really know how much acid or base you have. Okay, so let's take a look at a problem where we're going to standardize first and then do a titration. So here we have this idea where we want to standardize an acid by titration. So sodium carbonate is a base. It's a solid. This is an ionic compound, and we know that ionic compounds are usually solids. This is a base, and an accurately weighed sample can be used to standardize an acid. So we're going to use this to standardize aqueous hydrochloric acid. So we're going to say HCl plus sodium carbonate. Now this is an acid-base reaction, but it's also a gas-forming reaction, and we would call it a gas-forming reaction. Now we know that for this CO3 we need 2 hydrogens, so I'm going to put that here. And this would make H2CO3, which turns into H2O plus CO2. Now the leftovers are 2 sodiums and 2 chlorides. So you write that way with a 2 in front. So here's the balanced reaction. And we're going to start off with a sample of 0.263 grams of this sodium carbonate. And we're going to titrate it with 28.35 mils of aqueous HCl. And we want to get the concentration of the HCl solution. So we're going to start off with 0.263 grams of sodium carbonate. We're going to convert that into moles of sodium carbonate. And we're pretty sure we want to do that because when we transfer information from the sodium carbonate to the HCl, we're going to have to do a mole-to-mole comparison. So we'll turn that into moles of HCl, which will then turn into liters of HCl solution. And here, let's see. Actually, now that I think about it, we'll get the moles of HCl solution. And here, we're going to use the liters of solution. And I should say, we're going to take the milliliters of solution, turn that into liters of solution. This, along with the moles, will give us the molarity of the HCl, because we're going to use one of those C times V's. So we're going to have to feed into this the liters of solution. And we can work that into the same problem. So let's see how this works. 0.263 grams of sodium carbonate times the molar mass of sodium carbonate is 1 mole of sodium carbonate. I want to say this is 105 point something. So let's find out. So 2 sodiums is 22.99 times 2. 1 carbon is 12.01. And 3 oxygens is 48. So 105.99 grams of sodium carbonate. Next, we want to turn this into moles of HCl, so we use our balanced reaction, where we have 2 moles of HCl to 1 mole of sodium carbonate. So there we go, 2 moles of HCl to 1 mole of sodium carbonate from our balanced reaction above. And then we're going to multiply by, let's see, this will give us moles. So here, I'm going to just do this, 1 over this number here, let's see, 28.35 milliliters of HCl solution. Okay, now that seems a little awkward, but it's really fine. We're just introducing a new unit to this, and we don't want milliliters, so I'm going to write 1,000 milliliters of HCl solution over 1 liter of HCl. Oops, I don't like that little tail there. So we get that. Okay, now if you don't like doing this, we could start this another way. We could say, well, you know what? We're going to start with 0.263 grams of sodium carbonate, and we know that that's going to get us moles of HCl. And we know in the bottom, we're going to need the volume of HCl, so we're just going to go ahead and start with 28.35 milliliters of HCl solution. And our pathway might be, okay, I'm going to adjust this up here and put the 28.35 milliliters of solution. We could say, well, the top, we're going to do the moles, and we're just going to get rid of all of that. And on the bottom, we're going to turn that into liters of solution. And if the top is in moles of HCl and the bottom's in liters, you got the molarity. So this is what it would look like that way. So either way, you'll get the same result. So let's see what the estimate of the answer is going to be. Does everyone agree that 100 will go into 1,000 about 10 times? And 10 times 2 is 20. And 1/4 of 20 is about 5. And 5 divided by 28.35 is like 1 in 6. So that makes it about 0.15. All right, so let's see what we get here. Clear. 0.263 times 2 times 1,000 divided by 28.35 divided by 105.99, and we get 0.17 Looks like 3 zig figs, so 5 milliliters of HCl solution. So this is a standardized hydrochloric acid solution. We know its concentration. Now, honestly, we wouldn't be satisfied with one titration. We do this about 3 times and average it. Okay. Let's take a look at another problem now. So determining the molar mass of an acid by titration. So in this case, we have a 1.056 gram sample of an unknown organic acid, HA. Now this is important. When they say HA, it looks like there's one hydrogen for this acid. It's monoprotic. It's titrated with standardized sodium hydroxide. Calculate the molar mass of HA, knowing that the acid sample reacts with 33.78 milliliters of 0.256 molar NaOH according to the equation HA plus NaOH gives you NaA plus H2O. So here's the counter ion to the H. It's an anion, so that's why you have NaA over here. Okay, so calculate the molar mass of HA. So to calculate the molar mass of HA, it seems to me that we need to know the moles of HA, right? And the grams of HA. So eventually we want to get grams of HA on top and moles of HA on bottom, because that's the molar mass, whatever X is up here. So this is where we want to get to. And here we have 33.78 mils of 0.256 and a 1.056 gram sample. All right, so here if we take a look, I think this 1.056 is what we use on top. All right, so I don't want to start with that. I kind of want to end with that on top, and I would like to calculate how many moles of HA are in here. So I'm thinking to myself, to calculate the moles of HA, maybe I start with my 33.78 milliliters of sodium hydroxide. I turn that into liters of sodium hydroxide because I want to get moles of sodium hydroxide. And I can do that because I have the molarity of sodium hydroxide. For my balanced reaction, I can get the moles of HA, then I can plug that into this formula here, and we're good to go. So I'm going to do a kind of little nifty thing here, if you will. I'm going to go ahead and start with 1.056 grams of HA on top, and I'm going to start with 33.78 milliliters of sodium hydroxide on the bottom. Why am I starting with that on the bottom? Well, to get the molar mass, normally you get grams per mole, and I know I can start here and turn that into moles. So here I'm going to multiply by 1,000 milliliters of sodium hydroxide. And here I didn't write solution, but I'm going to write it now. Times 1 liter of sodium hydroxide solution. And of course, the reason we do this is because the molarity is in moles per liter. Now I'm going to write down this concentration right here. And I'm going to put the 1 liter of sodium hydroxide solution on top so that these units cancel. Boom, boom. But that means I have to put the 0.256 moles of NaOH on the bottom. These also cancel. And now I'm going to multiply by, let's see, the mole ratio. So the balanced reaction is a 1-to-1 ratio. So I'm going to put 1 mole of sodium hydroxide to 1 mole of HA. And these cancel, and I'm going to be left with grams of HA over moles of HA, which will be the molar mass. So let's go ahead and estimate. 1 times 1,000 is 1,000. 1,000 divided by 33 is tough. 33 goes into 100 3 times, so it should go into 1,000 30 times. Now, 30 divided by 2.256, that's a tough one. And it's making me realize I wish I'd done this a different way, and it's not too late. So I'm going to do it a different way. 33 goes into 100 3 times, so it goes into 1,000 30 times. 0.256 is like a quarter, and this is like a buck. A quarter goes into a buck 4 times, so I have 4 times 30. 4 times 30 should be around 120. All right, so that should be approximately the molar mass. Let's see what we get here. So we have 1.056 times 1,000 divided by 33.78, whoops, 78, and also divided by 0.256. And we get 122. Our guess was like 125 or something like that. So we get, or 120, I should say. So 4 zig figs, 4 zig figs, 3 zig figs. So 122 grams of HA per 1 mole of HA. So that is the molar mass, 122 grams per mole. All right. Let's put that to the side. And I believe we have one more problem to look at. We're going to use an oxidation reduction reaction in a titration. Let's see if we can see that title. So again, titrations don't always have to be about acids and bases. So let's read through this. The iron in a sample of iron ore can be converted quantitatively to iron 2 ion in aqueous solution. And this solution can be titrated with aqueous potassium permanganate. The balanced net ionic equation for the reaction occurring in this titration is MnO4 negative, that's permanganate, reacts with 5 iron 2 ions and 8 hydronium ions to give you manganese 2 ion, iron 3 ion, and 12 H2O. Now, you do this titration basically looking at the color here. I should say another way to do this reaction is with spectrometry, where you use a Beer's law type of thing here. And we'll probably be talking about that in the next section. So a 1.026 gram sample of iron containing ore requires 24.35 milliliters of 0.0195 molar potassium permanganate to reach the equivalence point. What is the mass percent iron in this ore? So if we look at what we have down here at the bottom, so we can shove most of this up here and focus just on the reaction and the numbers that were given here. You can see that the question really here is, what is the mass percent iron in the ore? So mass percent iron is going to equal the mass of iron divided by the mass of the ore times 100%. And the mass of the ore is equal to 1.026. So we're actually halfway home to solving this part because we already have the mass of the ore. So how do we get the mass of the iron? Right, that's what we want to get here. Well, I imagine to get the mass of the iron, we're going to need the moles of the iron, right? And I imagine to get the moles of the iron, we have to somehow use this equation to get the moles of the iron. And here you can see we have 5 moles and 5 moles, so it doesn't matter which of these two we get, it'll be the same answer. So how are we going to get the moles of iron? Well, you'll notice we're using the potassium permanganate, so I imagine we need the moles of potassium permanganate. And really, we don't see potassium permanganate up here, but that is the permanganate ion. So I'm going to put in little quotes here, moles of permanganate would be the same thing, right? Because if you look at the mole ratios here, it's a 1-to-1. Okay. And here, how do we get the moles of the permanganate? Well, I imagine we're going to take this volume and this concentration to get it. And I'm thinking here, since this is not a ratio, I'm going to start with the 24.35 milliliters of the potassium permanganate, turn that into liters of potassium permanganate, and then turn that into moles of potassium permanganate using the concentration. So if we're a little worried about this guy right here, are these really the same? We can take care of that. Now I'll show you how to do that. Okay, so here we're going to do 24.35 milliliters of KMnO4 times 1 liter of KMnO4 per 1,000 milliliters of KMnO4. And you can see I've given up writing solution after that. But if you want, I can slip it in right there. And then here, we're going to use the molarity of the KMnO4, and I'm going to put 0.0195 moles of KMnO4 per 1 liter of KMnO4 solution. Now, in the balanced equation, we don't have KMnO4, we just have MnO4. So I'm going to go ahead and change this to MnO4 and say that I have 1 mole of MnO4 per 1 mole of KMnO4. So if you take a look at one of these, you can see that, boop, if I cover up the K, I have one of the above. Okay, and so now I'm going to multiply by, and it doesn't matter which one of these we use. I'm going to say 5 mole of iron 2, 5 mole of iron 2 to 1 mole of MnO4. And then I'm going to go further, and I'm going to put that I'm going to have 5 mole of iron to 5 mole of iron 2. Or I could put 1 mole to 1 mole, it doesn't matter. Okay, now I'm going to be able to get the mass of iron 2 because iron has a molar mass of, I want to say 55.85. Yep, so times 55.85 grams of iron per 1 mole of iron. And that should give us our grams of iron. Now, do we really need this step? No. Do we need this step? No. So we could have done this instead, 24.35 milliliters. And I'm going to do this so it's easier for me to write. I could have written 24.35 milliliters of KMnO4 solution times 1 liter of KMnO4 solution per 1,000 milliliters of KMnO4 solution times 0.0195 mole of KMnO4 per 1 liter of KMnO4 solution. And I don't really need this. I can see that I'm going to have 5 mole of iron to 1 mole of KMnO4 because that MnO4 represents KMnO4. and then times 55.85 grams of iron per 1 mole of iron. So again, I'm going to estimate because that's what we do. And let's see here. 55 will go into 1,000 10, 20 times, right? 20 times. So we have 5 over 20, which is the same as 1 over what, 4. So we have 4 here. 4 will go into 24 6 times. And 6 times 0.1 would be 0.6. And actually this is 0.02. So 6 times 0.2 would be what? 1.2. So 6 times 0.02 is going to be 0.012. So we expect the answer to be around 0.012 if I've estimated correctly. Okay, so let's give it a try. So I'm going to turn this on, I'm going to clear it, and we're going to put 24.35 times 0.0195 times 5 times 55.85 divided by 1,000 divided by, 1. I'm going to put 1 because it won't change anything. And we get 0.132. So I did a little wrong thing because I thought it would be 0.012, but this seems like it might be right. Where did I go wrong? Oh, I know where no, I don't. This will go into that 20 times. 5 will go into 24 times. 4 will go into that 6. 6 times 0.0195. Oh yeah, that would be 6 times 0.019. I said the answer would be around 0.012, but that's ridiculous because 0.012 is smaller than that. So 6 times that, it makes more sense that it would be 0.12. All right, so I'm a little off on my estimate, and it's always good to double check these things. So here, how many significant figures are we allowed? Because of this, 3. So 0.0132 grams of iron. Now, is that our answer? The answer is no. They didn't ask for the mass of iron. They asked for the mass percent. So we have to finish this off by saying the mass percent iron is equal to 0.132 grams of iron over the mass of the ore, which is 1.026 grams of ore, times 100%, which is equal to, so divided by 1.026, and then times 100, and we get 12.9% iron in the ore. And there's your answer. Okay, that was the last problem example in this particular section. Thank you for listening. And we do have one more section, and that section is spectrometry. Stay tuned.